should end. It's 8:30 on my Central European time clock. So welcome everyone to this session. And without further ado, I will let Paul to introduce himself and give a talk. Thank you, Paul, for being here.
Sure thing. So it's an incredible privilege and honor to be able to speak with you right now for the Life in Space conference. It's been some very interesting talks about extremophiles. I've learned a lot. Looking forward to hearing more about biosignatures and then about prebiotic chemistry and a variety of other things tomorrow. I'll be talking about disequilibrium and the abiotic baseline. This is a particular term that was coined by Kevin Heng, actually, and has started to be applied by a variety of people looking at the difference between what biology does versus a particular background. This is work that I've been involved with Oliver Shortall, and so I give him acknowledgement on this front slide. This is work that's been done at University of Cambridge in association with this Leverhulme Center for Life in the Universe. Please Google that if you're interested. There's a lot of interesting things that I think relate a lot with the interests of this conference going on at Cambridge with this particular center. And please do feel free to reach out to me via email or reach out to the center if you'd like to be a little more involved with that. So the sort of story that I'm looking at, you can look at this from an exoplanet perspective. So I'm thinking about planets around other stars, other systems of planets. How could we tell that there might be life on these particular planets? You would maybe look for certain things in their atmospheres. So this is a real color picture of Earth's atmosphere with the moon, as you see in the background. Beautiful picture. This is what this looks like at roughly 8.6 microns. And then if you switch to 9.6 microns, you end up with this ozone. So you end up seeing something that absorbs light in this atmosphere. If you were to look at this planet as it was passing in front of its star, and you have a large enough telescope and good enough resolution, and you're looking at spectra, the size of this planet would change based on what wavelength you happen to look at. And if you happen to look at 9.6 microns on a planet with a fair amount of ozone, the planet would actually look a little bit bigger in that wavelength because a bit more of the light from its atmosphere is being blocked. If you looked at it in emission, you would see a particular feature that way as well. And so this is actually a picture of this sort of relative flux. This is a nice paper by Palais et al. 2009, which is Earth's transmission spectrum from lunar eclipse observations. And so what you can see here is you can see ozone and oxygen and methane. And it's particularly the sort of oxygen and methane, often called a sort of redox disequilibrium pair. You would imagine that the oxygen, the O2, and the methane, the CH4, would react with each other and form CO2 and water. They wouldn't be stable in this atmosphere long term. And there's a more general way to look at this kind of disequilibrium. And a lot of the ideas about looking at the sort of disequilibrium or as a biosignature originate with people like James Lovelock. So James Lovelock has this paper, Thermodynamics and the Recognition of Alien Biospheres, where he specifically looks at these thermodynamic properties and argues that life has this almost unique ability to sustain at least a certain degree of disequilibrium in a planetary environment. And in the context of this talk, we'll be talking about planetary atmospheres, largely because that's often what you can see the best for planets outside of our solar system. So if we're going to look for life there, that's roughly what you would be looking at. So what does this mean, again, disequilibrium as a biosignature? It turns out that this is quantifiable. And it's quantifiable in terms of the Gibbs free energy, which is measured in kilojoules. It's a measure of energy. The Gibbs free energy is most appropriate applied to places like atmospheres because it's a thermodynamic quantity holding temperature and pressure as constant. And you can define it in this way. This is the partial molar Gibbs free energy of a particular species. So this is the Gibbs free energy for that particular species. There's a gas constant and a temperature. There's an activity of the species which is closely related to the concentration of that species. In most circumstances, in some circumstances it diverges. If you want to know more about that, please leave something in the Q&A. I'll be happy to get into what activity actually is. But for our purposes, we can treat it as a sort of analog to the abundance of a species. And in fact, at the very end of this, we do have the abundance of the species right there. And what chemical equilibrium means is if we end up summing over all of these, given the sort of atoms that we have, if we keep rearranging these atoms in all these different ways, we can find a certain arrangement of atoms that gives you your minimum Gibbs free energy, the smallest Gibbs free energy, and that's what chemical equilibrium means. This is thermochemical equilibrium in this case, TCE. And so disequilibrium as a biosignature could be looked at as this Gibbs free energy, the actual real Gibbs free energy in a particular environment, minus the thermochemical equilibrium's Gibbs free energy. So this would be your measure of disequilibrium that you would want to look at. But the problem is that we don't know these. We don't know either of them. In fact, even in planets in our own solar system, it can be very, very difficult to really constrain either of these. So one of the things that we can do, of course, is we can replace the first term with the Gibbs free energy just based on the observations. We see some molecules, we probably don't see all of them. We may not even see the most abundant ones, but maybe we can try to infer those. And so we can get a sort of guess at what the observed Gibbs free energy happens to be. And then we can subtract that by the thermochemical equilibrium, the actual thermochemical equilibrium. The problem there is we don't really know that either. Thermochemical equilibrium will be dependent on pressure and temperature, which we may not have very well constrained in a particular atmosphere, certainly on a surface of a particular planet. And also, it will depend on what atoms are available, and that will also depend on observations. So what we really are doing is we're kind of hoping that, again, the sort of observations kind of mimic or at least approximate the actual real. And that also we can kind of approximate what that chemical equilibrium is. So assuming that we can get good approximations of these from observations, this will give us a degree of disequilibrium. And this particular formulation and some of the other things I'll be showing later on in the paper, later on in the talk, can be seen in this paper by Josh Christensen-Totten et al. In astrobiology. So we could look at disequilibrium in Venus's atmosphere. This is the results shown in this particular paper. And you can see that when you start looking at the sort of surface abundances and what you would expect given equilibrium for these surface abundances, it looks like Venus's atmosphere is very close to being in equilibrium. And so if you're looking at a degree of disequilibrium as a sign of life, you would say, well, there's not much of a sign of life in Venus's atmosphere. But if we only had access, say, to observations above the clouds, or even if we just consider that the cloud chemistry is changing some of these, we can actually see that there are quite a few deviations. The OCS goes away because it gets photochemically destroyed. The SO2 and H2O are getting photochemically processed and then condensed out as sulfuric acid into the clouds. All of a sudden, this disequilibrium looks quite a bit larger, just because we become limited to only looking at a particular region of an atmosphere, and we make certain inferences based on that. In Jupiter's atmosphere, you can run into a sort of similar problem. I don't have it quite drawn up here, but we'll return to what photochemistry does to this. But Jupiter's atmosphere, again, looks like it's fairly close to equilibrium. Earth's atmosphere, interestingly, also looks like it's relatively close to equilibrium. You can find some small exceptions to that, methane being probably one of the more important ones, hydrogen also. Although hydrogen and CO2 in disequilibrium might be surprising if you would try to infer life, because you would imagine that life would try to use that particular kind of available energy through consumption and produce different kinds of disequilibrium. But in any case, you see this, and you could imagine someone who had these sorts of constraints debating about whether there was life there or not. But this is only if you consider the atmosphere. If you consider the atmosphere and ocean together, all of a sudden it turns out oxygen is in considerable disequilibrium, CO2 is in considerable disequilibrium, methane remains in considerable disequilibrium. But again, you would have to have some way of inferring that there was an ocean there and really looking carefully into what the ocean chemistry does before you would say that there was a substantial disequilibrium. So here's an example of something that looks like it's in equilibrium given our data, but there is life there. And then you can look at an example like Venus that looks like it's out of equilibrium, but there's likely no life there, at least given what we know presently. Photochemistry in Jupiter, actually, it turns out that if you were monitoring higher up in the atmosphere of Jupiter, the methane ends up getting photolysed and producing these larger hydrocarbons, which are all out of equilibrium. And those disequilibria are at least as extensive as the disequilibrium of methane in Earth's atmosphere. And so if you didn't consider the photochemistry and just looked at disequilibrium, you'd say that the disequilibrium of an oceanless Earth would be roughly equivalent to the disequilibrium of the stratosphere of Jupiter. Volcanic chemistry also can throw things out of equilibrium, because it turns out that the volcanic gases are assumed to be roughly in equilibrium. This is probably, at least overall, generally true. But they're in equilibrium at a particular temperature and pressure, which is not relevant for the atmosphere. And so when the gases get there, they get kinetically quenched. They just can't react because of these enormous energetic barriers. And so you end up with a gas that, again, is completely out of equilibrium, but doesn't involve life at all. And certain types of bizarre magma chemistry can combine with photochemistry to produce even larger signs of disequilibrium. For example, and this is something that I worked on, is looking at cyanoacetylene as a tracer of nitrogen chemistry in hydrogen-rich exoplanet atmospheres. You would see a lot of cyanoacetylene. No one would really say cyanoacetylene would ever be a good sign of life, but if you were just strictly abiding by disequilibrium and you could only see the sort of upper atmosphere, you would say that this is an enormous amount of disequilibrium. So I'm now going to recommend another modification. If you want to stick with talking about chemical disequilibrium as a biosignature at all, maybe we should just throw this idea out. I'm definitely open to that. But if you wanted to stick with this idea, I think there's a way to modify it so it could be more useful, which is that you now talk about what are the possible Gibbs free energies given our observations? What's a range of possibilities? You look at an ensemble. Maybe you do a sort of Markov chain Monte Carlo. You wander through the parameter space and get some ideas about that. And then you have another G, which is AB, which is the abiotic baseline. And this doesn't just look at chemical equilibrium, but the sorts of disequilibria that can be caused abiotically. Lightning, photochemistry, volcanism, impacts, all this other sort of stuff. Each of these would be an ensemble of values, and you'd have to look at this combination of all these different values to talk about how large your delta G could possibly be. And this discussion really isn't about what delta G really is, but what it probably is. And so you can look at these ensembles, you could weight them probabilistically, but this will require something like a Bayesian framework, starting out with some prior probabilities for disequilibrium, and then looking at what the posteriors are given the available data. I think a good example of this approach, although this approach doesn't really look at the Gibbs free energies directly. It still takes a sort of, I would say, conceptually related approach. And this is Baines et al. 2021, their astrobiology paper, which is looking at phosphine in the atmosphere of Venus. Jane Greaves, you're very, very fortunate to have her here to give a keynote talk tomorrow at 6:20 p.m. Central European time. What was done there is saying, well, let's say that we know that there's really phosphine there. What are all the abiotic ways we can figure out how this could be produced? How much does this result, this observation, deviate from all the abiotic ways that we know to produce it? And this gives you that sort of sign of disequilibrium. The sort of issue then is, do you really say that that disequilibrium is due to life, or do you just say that it's due to some unknown abiotic process?
Sorry, Paul, we need to finish.
And this is where I'm going to just finish right here. Is just a brief diversion about anomalies in multiple baselines. There's a paper that I wrote along with Carol Cleland, a philosopher who's been very, very interested in this sort of stuff, looking at ammonia and phosphine in the clouds of Venus as potentially biological anomalies, really saying that we should be agnostic about whether they're biological or not, especially in these sorts of environments where the sort of life that would have to be there, given the sort of prior probabilities, if there was life there, which seems like a low probability, it would have to be life as we don't know it. It's good to be agnostic and just look at these interesting deviations from our expectations, pay attention to them, don't ignore them, don't throw them out because they don't fit our particular paradigm. But then be open to the fact that they could be explained biologically and they could be explained abiologically, and then try to look further into those two sorts of classes of accounts while trying to maintain as much scientific neutrality as possible. So that's the sort of perspective that I have here, and hopefully this will just be the beginning of an interesting discussion or even debate about how these concepts really play out in the search for life elsewhere in the universe. Thank you very much for your time.
Thank you very much. That was an amazing talk. Unfortunately, we don't have time for questions, so I will move now to another speaker. That will be Anna. Once again, thank you again.
Sure thing.